All right, in this lesson we are going to introduce what we call polar coordinates. You guys are very used to working with what we call Cartesian coordinates. Those are also called rectangular coordinates. Those words are interchangeable, so just understand that you might see one or the other, but they mean both the same thing. Those are just the type of coordinates that you've been working with since middle school, if not before, okay? So for instance, over here, the coordinates of that point is just the distance that we've traveled from the origin horizontally, and then the distance that we've traveled from the origin vertically. So that x value is the horizontal distance from the origin, and this is nothing that we don't know. And that value of y is the vertical distance from the origin. So we get those coordinates by traveling horizontally and then up. So what we're going to talk about today are what we call polar coordinates. So these are defined as r theta. So if we look at defining that point in terms of polar coordinates, that first value r is going to be, so we kind of know it as the radius, which is what it really is. If you think about drawing a circle that goes through that point, that value of r is the radius. We also define it as the distance from the origin, or what we call the pole. So that origin we call the pole. That value of r is the distance from the pole. Or if you think about drawing that circle around, it would be the radius of that circle as well. The other part of a polar coordinate is theta. So that is the angle, as you can see here, that is measured counterclockwise from the positive part of the x-axis. So if you look at starting here, we have a rotation in this case of 22.6 degrees. So we would take the value of the radius, or the distance from the pole, 13, and we would take that angle measured counterclockwise, which in this case is 22.6 degrees, and just put those in an ordered pair. So one of the major things that we are going to be doing is converting between Cartesian coordinates and polar coordinates. And one is definitely easier than the other, so let's start with the easier of the two. And that is actually going from polar coordinates back to Cartesian. And again, Cartesian is the same thing as calling them rectangular coordinates. And what you'll find is we've really already been doing this. So we want Cartesian coordinates, meaning we want x and y. To find the x coordinate, we are going to take that value of r, the radius, times cosine of theta. Y is going to be r times the sine of theta. So these are both little formulas that we should definitely recognize and understand where they come from. So let's go ahead and take a couple minutes to look at a couple of examples giving the Cartesian coordinates from the given polar coordinates. So again, given is r theta. To find our value of x, we take 7 times the cosine of pi over 3. Anytime that you have an angle that is a unit circle angle, you are definitely going to give the exact value. So this is 7 times 1/2. Cosine of pi over 3 is 1/2. So that x coordinate is 7 over 2. Similar thing for y, we're going to take 7 times the sine of pi over 3. again, using our unit circle to evaluate sine of pi over 3, which is radical 3 over 2. So we're going to write this y coordinate as 7 radical 3 over 2, and then finally just taking those two values, writing them in an ordered pair. If we look at the next one, same type of thing. So we are given value of r, angle of rotation, theta. We want our values of x and y, so I'll take 5 times the cosine of 0 for x, 5 times the sine, oops, that should be 0, not theta, 5 times the sine of 0 for y. So again, unit circle value, you need to be giving that. Cosine of 0 is 1, so our x coordinate is 5. Here, sine of 0 is 0, so the y coordinate is 0. Notice that these appear to be exactly the same, but understand that they're giving different information. So this is the distance you've traveled horizontally and vertically. This is the radius that you would have in the angle of rotation. So they look the same here, but understand they're really giving different information. All right, what I would like you to do is stop the video. I want you to go ahead and try this last example. That is pi there. And then once you turn the video on, you can check your answer. So you should have -5, 0 using y equals cosine of pi, excuse me, x equals 5 cosine of pi and y equals 5 sine of pi. The more difficult of the two converting is going then from Cartesian coordinates to polar coordinates. So starting by finding that value of r, we are essentially going to take the square root of x squared plus y squared. And that's really just coming from Pythagorean theorem is where that's coming from. And then we are going to find our angle theta by taking the inverse tangent of y over x. Now, this is the part that's a little hard because there's a couple of special notes and stipulations that you have to keep in mind for that. So let's go ahead and write it down, and then once we get to the example, we'll see how this works. If you end up with a tangent value in here that is an exact value, meaning it's on the unit circle, you are just going to use that value from the unit circle. And we'll see again what this means once we get to an example. If that value is not exact, here's where it gets a little tricky. If that value is not exact, and your point is in the first or fourth quadrant, you're just going to use the calculator value. If it is in the second or third quadrant, you are going to use the calculator value and add pi. And we'll talk about why that is once we get into it. So if you look at the next page, we have some examples converting from from Cartesian to polar coordinates. So again, let me just write at the top here. So finding that value of r, square root of x squared plus y squared. Finding that angle theta that we need, inverse tangent of y over x. So we'll use those here with this first example. So this given is our x and our y. So starting off finding that value of r that we need. Take the square root of 3 squared plus 4 squared, and then just simplifying from here. So that value of r that we need is 5. From there, I'm going to use inverse tangent of y over x, which in this case is 4 over 3. Now, going back to what we just talked about on the last page, because this is not an exact unit circle value, we're going to use our calculator. So if you use your calculator to find the inverse tangent of 4 over 3, you end up with 0.927. So then the last thing that we have to consider is what quadrant this is in. So just think about that original point, 3, 4. 3, 4 is in quadrant 1. In quadrant 1, we keep the calculator value. So we're just going to stick with that 0.924, or 27, sorry. So then we take our two values that we have and write them in an ordered pair, 5 and then 0.927. Okay? All right, so I have taken up all my room, so I'm going to erase this, double check that you have this down before I take it all away. All right, in the next example, again, let's start with finding that value of r. So I'm going to take 0 squared plus -5 squared, and then simplify. So again, we get that r is 5. And then here, using that inverse tangent to find theta, I would take -5 over 0. Now, when you put that on your calculator, you're going to get an error. Well, why are you getting an error? Hopefully you see that you're getting that error because you have a 0 in the denominator of that fraction. But that's perfectly fine because there are tangent values that are undefined. Okay, that's where you have those asymptotes. So here's where you have to figure out which of the angles this is that's undefined. So go back to your original point, 0, -5. 0, -5 is right here. If you were to graph that, that corresponds to the angle in which this tangent value is undefined. So in terms of theta, that angle is 3 pi over 2. So again, I just take my two values, 5 and 3 pi over 2, write them as an ordered pair. All right. Last example, actually, why don't you guys go ahead and try this one and see what you get. You should have gotten your value of r to be 2 radical 2, and then your value of theta, 11 pi over 6. So you might be confused on this angle just a bit. So we take the y value over the x value. Radical 2 over radical 6 is 1 over radical 3. Then when you rationalize that denominator, that's negative radical 3 over 3. Well, tangent is negative radical 3 over 3 at 11 pi over 6. Okay? All right, next little thing that we are going to talk about is the fact that there are multiple polar coordinates for any one point. And that is because you could take this point P and wrap it around the circle in either direction once, multiple times, okay? Typically, though, you are going to give the angle between 0 and 2 pi. So for instance, the first thing that we need is the value of r. So 1, 2, 3 is the value of r, and then this is along the angle pi over 4. So this is typically the polar coordinates that you would give. If you were to wrap or rotate your point around the circle one more time, we would be adding 2 pi to the angle. The value of r stays the same, and then if we add 2 pi to pi over 4, That gives you 9 pi over 4. We could do a similar thing rotating it the other direction. So in this case, you would be subtracting 2 pi. Again, the 3 is the same. And then pi over 4 minus 2 pi gives you negative 7 pi over 4. Okay? All right. Next, looking at graphing in polar coordinates. So the first thing that we are going to do when we graph is we are going to first find the angle theta. After we find the angle, then what we are going to do is we are going to locate where R is on the terminal side. Of theta. So do the angle first and then the radius. I know it seems kind of backwards, but so for the first one, point A is 30 degrees. So 0 degrees is right here. So along that terminal side of the angle, I'm going to count 1, 2, 3 units. So point A would end up right there. For the next one, point B, this is where it gets a little tricky. So the angle 180 degrees, the terminal side of that is right here. But notice that that value of R is negative. So I'm not going 7 units that way, I'm actually going 7 units in the opposite direction, which leaves me right here. So terminal side is here, but with a value of R of negative 7, it's like I'm going backwards 7. So B would actually be right here. C then, I have to locate the angle negative 45 degrees. Negative 45 degrees is right here, and then 7 units along that terminal side leaves me right here. Go ahead and try the next 2, or 3, I guess, on your own. So stop the video, plot them, then come back and check your work. Double check that you have your points in the correct place. So D for negative pi over 4. Negative pi over 4 is here, along that terminal side, 4 units. Point E, 2 pi over 2. So pi over 2 is here, 2 units up. And then F is probably the toughest one. So you need to go to negative pi over 3, which is right here. And then you are going, oh, I went too far. You are actually just going 1 unit from there. So F should be right here. All right. Next thing, and really the last thing here. There are several different types of curves formed by graphing in polar coordinates. So I just went ahead and put in a graphic that shows you a couple of the most common, the cardioids, the roses, different things. So let's say, for example, let's take this rose, for example. Let's say that you were asked to graph R equals 3 cosine of 2 theta. First of all, you know that you're graphing in polar coordinates because it's R equals. So what you need to do on your calculator is go to mode, change your mode to polar, which is POL, and then once you go to your y equals is now R equals. And then you can just type in your function. And then what you need to do after that is go to your zoom, choose zoom 7, which is trig, and that automatically fits your window to what we need. And then you'll see a pretty little rose.